Welcome to another episode of Code for Thought. CERN, the European Nuclear Research Centre, located on the outskirts of Geneva in Switzerland, is known the world over for its groundbreaking research in fundamental physics. A number of profound discoveries about the nature of matter were made there, such as, for instance, the discovery of the W and Z bosons in 1983, which are particles, in case you wonder, that are responsible for the so-called weak interaction, which is one of the four fundamental forces. And of course, let's not forget the discovery of the Higgs boson, announced in 2012, named after the British physicist Peter Higgs, who sadly passed away in April this year, 2024. And this year, CERN is celebrating its 70th birthday, and I had the privilege and the pleasure to attend an event in February this year, 2024, called the Third Collisions, organized by the indefatigable community team around Rachel Bray. The event was for CERN alumni, and the reason I was there is that in my spotter youth, I was one of the PhD students who worked at a small experiment at CERN studying collisions between antiprotons and protons at low energy. The experiment was called Crystal Barrel, and it was, compared with some other detectors and experiments, quite small. The detector, of course, is no longer there. It was dismantled sometime around the late 1990s, although the ring that used to provide us with antiprotons still is. Well, kind of, because now it's feeding experiments with heavy ions instead. Which is a reminder that in addition to big experiments like ATLAS, CMS or LHCb, CERN is also host to a large number of medium to small-sized experiments and research projects. Making all of that possible is a sophisticated infrastructure and a team of dedicated researchers, technicians, administrators, and of course the reason for this episode, software engineers. Which brings me finally to my guest for this episode, Spyridon Trigazis. Spyridon is taking us behind the curtains and offers us a view of what it takes to keep the complex projects and infrastructure running. To help with that, a decision was made to move to tools like OpenStack and Kubernetes. And in our conversation, we focus on the challenges that it brings when rolling them out across a campus with such a vast and diverse set of teams and projects. And while talking about it, I hope you also get a good glimpse and impression what work and life at CERN looks like. And so, without further ado, here's Spyridon. Hello, Spyridon. Thank you very much for your time today and welcome to the show. Let's start with introductions.
Thank you for having me. I'm Spyridon Trigazis, Spyros in short in Greek. I studied in Greece computer science in the Aristotle University of Thessaloniki, where I did also a master's degree there in data management. And then while I was in the university, I was also working in the IT department of the university for some time in user support and reporting. And during my master's, I did what is quite important, I think, for young viewers, listeners as well, is I participated in a Google Summer of Code program in 2013, which was in a cloud infrastructure project used internally at Google, but also in the Greek research community and other communities. And then I applied as a fellow at CERN in the general pool, and I was selected to work in the cloud infrastructure of the CERN IT department. This Google Summer of Code experience was quite nice for me. My mentor was at Google actually, which is not usual for a GSOC program. But this interest started when I was a master and almost finishing my bachelor's program, because to have access to bigger machines and have a distributed system, I was using public clouds or even the semi-public cloud of the Greek research community. And I developed an interest in that, which eventually manifested to doing the GSOC and then being selected to work in the cloud infrastructure at CERN.
So what made you go to CERN in the first place?
Initially, it was also idealistic reasons. I didn't want to go work directly for a commercial company and work only for money. Maybe I would have been richer now, but in experiences, probably not, because I wanted to do something to give back to the community, in the most European countries, and there are other countries that are participating at CERN, to my host country as well. I like the academic style of working. Also, I was quite fond of open source software, and there were many opportunities in an organization like CERN to work on open source. And even if it's not exactly open source, it's just open code to others, it's also nice that it's academic environment. We can share what we do. There are no secrets or things that we can or cannot talk about. So even participating in the communities, it's much easier from an organization like CERN, because it's our obligation in a way to share what we know about not only physics, but all the other aspects of our work.
I find this quite interesting because cloud infrastructure, people are familiar with cloud infrastructure through the big commercial companies such as Amazon Web Services, of course, which is the biggest, Google, which you mentioned, where you went to a summer school, and then there's Microsoft Azure, or Azure, I never know how to pronounce this. But then at CERN, you're not using any of that, are you? You're using a different infrastructure.
So actually, we do use the public clouds as well. There are a few use cases. There is also other activities that are going to invest more on usage of public cloud. But CERN is an old organization, and CERN in the early 2000s had one of the biggest data centers in Europe or in the world before the boom of the IT companies like Google and Facebook. That Google, when CERN had a big data center, had a garage. So in-house, there is the culture and there is the knowledge and there is the infrastructure already. So for an organization like CERN, it's feasible to have a data center. And of course, also there are the demands, the huge amount of data that we have, which is many petabytes. And I'm not sure about the numbers because it's the storage team that manages that. But we have a big infrastructure for tape storage to store physics data. So there is for sure the need to have infrastructure here. And because of that need, we can also have a cloud infrastructure. And if we talk about numbers later, we can see that we have a cloud infrastructure, but it's not the majority of the compute capacity that we have.
Yeah, we can come back to that maybe a little bit later. But what I would like to move to is OpenStack. And I think that's an area, OpenStack and Kubernetes, which is what you're involved with.
Yes.
So could you give us an overview of what OpenStack actually is? And this is the reason why I mentioned commercial companies before, because it actually sits quite separately, doesn't it?
Yeah, exactly. So apart from using some services already in the public cloud, we have quite some infrastructure which is based on OpenStack. OpenStack is a collection of open source projects, which are community projects under Apache license version 2. And it started initially in 2010 or 11 by private or public cloud provider in the US in collaboration with NASA. It has only one project initially to provide virtual machines and some basic networking. And then it expanded, like branching out components, how to manage the images of the virtual machines, how to manage the network, how to manage the VM, but only the compute part of the VM, then storage, then orchestration, then containers, databases. There is almost everything. This was good and bad. It was very good when there was a lot of momentum, a lot of contributors, and having everyone under the same project would be non-trivial to manage. And there was a big push from companies. They were putting a lot of money so that they influence a lot. I wouldn't say control because no one tried to take over, but to influence a lot the projects. So they started breaking to smaller components. And now we're at this state that we have like the core of OpenStack, which is 5 or 6 projects. And then there are additional optional add-ons. So OpenStack at CERN started around 2012 before me joining the organization in 2016. The team then was running some infrastructure for virtual machines based on some Microsoft product for on-prem hosting. And I think for license reasons and because they wanted to expand more and add more features and have more options to customize it, they had a look to OpenStack. It looked promising. It had a lot of momentum, a lot of traction, and they started investigating on it. And then it took off in the department. It also helped to redesign how services are run in the data center to standardize monitoring, configuration management.
Mm-hmm.
And then later on, Kubernetes appeared in 2015, and containers as well became more popular and easier to scale in many machines. With Docker, like Docker was excellent to work on your laptop and 1 or 2 servers. But when you wanted to have thousands of them, it was non-trivial to orchestrate something with very fast rotation of components, meaning deploying new software very frequently, wanting to have uniform monitoring and so on. So in 2015, Kubernetes started. Again, it was another cycle of hype in the IT sector. A lot of companies jumped in. It gained a lot of traction. Core idea of the project was really good and really straightforward to work on it, even to do contributions or use it. And we started adopting it to eventually leverage containers and immutable infrastructure that you build once, deploy everywhere. Everywhere it's, of course, terms and conditions apply, but it's almost everywhere. And then other important parts are auto-scaling, fast scaling to add more components, observability, and the GitOps practices, and security as well, where Kubernetes helps a lot, like standardizing how to run processes, not even just applications or servers.
And OpenStack is now adopted at CERN as well as Kubernetes, but I think you had to put quite a bit of effort in it to adopt it to your needs at CERN, didn't you?
Yes, and this can happen when you are not starting from scratch and you already have a data center. Most importantly, for people working in IT departments, if there is already a network team present that has set some standards, you cannot break those. It's very hard because, for example, the networking team, apart from the data center, is responsible for the campus, is responsible even for the small hub that providers are using in the commercial providers that are using at CERN, or the other sectors or the experiments. So these components must work and the new things must be adapted to what we have. So our data center was an old data center. It had already a layout of the network, which was a flat network, and OpenStack, the deployment of OpenStack had to be adapted to that because OpenStack was designed with best practices and modern data centers, which would require multiple network interfaces, one for storage, one to manage the services only for admin, one to serve user workloads, one, more secure and air-gapped environment. So it had quite a few requirements to be able to run the standard or the reference architecture. So we had to adapt to our architecture of the data center and then also integrate with the existing identity system we have at CERN, which was not very difficult, but we had also to adapt a little bit for that as well. While new deployments could just adopt whatever the upstream project was giving and use it as is.
I think that's quite interesting because CERN is not a monolithic organization. There are a number of experiments running. I don't know how many experiments they're actually running. We certainly know the big ones like Atlas, CMS, and LHCb, but the experiment that I was involved with at the time was a very small one, and there are lots of them. So it must be quite a challenge to actually roll out an infrastructure with OpenStack and Kubernetes like that. I mean, how do you manage that, and what is your involvement?
So when OpenStack started, accounting was quite a challenge because OpenStack was designed to be used in a monolithic way or in a way where you are a public cloud. There are some public clouds in Europe and in the US and elsewhere that are OpenStack deployments. And then the more you use, the best is for you that you're on the cloud because the customers will pay. In our case, we buy the hardware and it must be used fully, but only for the people that should use it. So this creates challenges about allocating quota and resources to different teams and then making sure to claim them back and then give access again, shrink or expand the capacity. So this was quite a challenge. And for that, every experiment has a coordinator, a computing coordinator that is tasked with that. And as well, all experiments, the big ones have a dedicated coordination meetings with IT. And the smaller experiments, they go all together in one coordination meeting because the needs are smaller. Because when we say one big experiment, for example, CMS, it's not only one team, it's many teams. The big experiment is a collection of smaller experiments, we can say. And then With Kubernetes, it was easier in a way from a different angle because we could consolidate resources. So more teams within an experiment could use the same cluster, and then the abstraction and management of resources could move there. For example, to talk specifically for cores and RAM every application is using, rather than I want this many core and RAM and disk to create first virtual servers and then deploy inside them the processes. It's like an overhead, not only in work, but also in resources.
Give us a feel for what the resources are that you have. So how many nodes, for instance?
So with OpenStack, we are managing almost 10,000 physical machines, but 1,600 of them are hypervisors that run virtual machines. The rest are storage nodes, and the biggest chunk is batch compute to run batch jobs for the experiments. Like 80% of the capacity of these physical machines are dedicated to the batch system. And 10%, maybe less than 80 is batch, and around 10% is storage, and the other 10%, roughly, or 15% is the cloud infrastructure. Then in the cloud infrastructure, we have 14,000 virtual servers.
40 or 14?
14.
14, okay.
Yes. And in CPUs, we have 500,000 physical CPUs, and only 100,000 of that is virtual servers. So the vast majority is physical machines. And OpenStack there helps to streamline the provisioning and the reinstallation of machines, to have like an API to just trigger the reinstallation of the servers and shutting them down and on, and have an API to manage that. And in terms of RAM, it's quite impressive. Even when I look at it, it's 2 petabytes of RAM in all the physical machines.
It probably has to be, because it's quite compute intensive.
Exactly.
And I'm thinking about the experiments again. I went on a tour, so there was an alumni event in 2024 that I went to, and we went down to see LHCb, where they do the beauty quark physics. And the amount of data that come out of an experiment, I don't think they use any hardware triggers or something like that. Anyway, the amount of data that come out of it is just mind-blowing. And how can a system like that cope with the sheer amount of data that come out of experiments once they're running?
One of the most impressive systems that CERN is running is, I think, the detectors. And talking about compute is the trigger farms and online farms the experiments are running. These are not run by the IT department. The experiments are managing those. And the big experiments have special hardware that compute with VHDL, for people who may hear that are into computer architecture. And they write the software directly in the device, which has a huge capacity to process events in terms of many gigabytes per second. And they can filter down to like 10 orders of magnitude the data, and then the data go to the online farm of the experiment, which is filtered down again, and then from all the experiments we get a fraction of all the sheer amount of data the LHC produces. And this data is stored immediately to the shared storage system called EOS that the storage team is managing, which is an in-house open source system. And then not experiments, but collaborations of the experiments can analyze at a later time the data at their own pace, do event reconstruction, try different simulations or different experiments to interpret the data.
You are also involved, moving on a little bit, you are also involved in the accelerator and technology sector, which I believe is a different department at CERN, isn't it?
Yes, it's actually more than one department. It's a whole sector. And the services that they run and the servers that they're running is at an air-gapped network. So they don't have the easy way of deploying services like we have in the IT department and in other departments. Everything is more controlled, and it's harder to get software in or new deployments. Traditionally, each team was what was the IT department before 15 years ago, that had some physical servers that they install and they run their applications inside, which means that every team has its own procedures. They have their own way of deploying and monitoring. And some teams in the ATS sector, in the B department, had the idea for start adopting Kubernetes to standardize the way everything is deployed, the way the metrics are emitted and they're collected, security standards, and distribution of the software, because the standard way at CERN was RPMs for CentOS-based systems, like the Scientific Linux and CERN CentOS. Right. Now we're moving to more standard like Alma, Rail, Debian, and there is an effort to adopt as well. But with containers is another way of shipping and even vet the software, what is running, what is included. Mm-hmm. So we started an effort to run some systems like a container registry based on Harbor from the CNCF to serve containers and OCI artifacts, which can be Helm charts, container images, even machine learning models. And as well, because we have the expertise already, we deployed also a small OpenStack deployment air-gapped from the rest that they can spin small Kubernetes clusters for development and iterate faster. Some use cases of that include the CI systems that they need to run to build software and do validations inside this air-gapped network.
That's continuous integration.
Yes, continuous integration, like builds and tests. There is, for example, the post-mortem system, which is a system to analyze events of the LHC. And they want to serve this Java application in Kubernetes to be able to do rolling updates of the software, and they don't have to wait for a technical stop to do a small change.
I think it's important for the listeners to point out there is not one accelerator at CERN. There are actually quite a large number of them.
Yep.
So there is the linear accelerators. I think there are two, I believe. Then there is the SPS, the proton synchrotron, and then the LHC, which is the one that people probably are more familiar with because that's the large ring.
And we also have a decelerator, which is the accelerator factory.
And so that department or that sector, accelerator and technology sector, that actually deals with all of these accelerators. And what you're saying is that each one of them have their own solution so far.
Yes. So they try to consolidate between them and follow the same practices. Not everyone is already on board. It's the example that I mentioned is from the teams that we are already collaborating with. One of the goals of this and next year is to end up with what the architecture should look like, and we are committed that this is the standard production system others can adopt. Because right now, all these teams that are keen on trying Kubernetes, they're also keen on iterating fast and changing as well.
So it's not only changing the infrastructure, it's also the way they work that changes.
That's the biggest change, yes.
Give us a feel for the kind of applications that these accelerated teams run and need. Because I remember from the experiments that back in the days, which is now over 30 years ago, we had this kind of monitoring system, how the beam composition and the luminosity and all of that. Mm-hmm. But I'm sure there's more involved in that than this.
To be honest, I'm more familiar with the teams that I have collaborated with, because also from what we discussed already, which ties nicely together with this question, is that when the adoption of OpenStack and Kubernetes started, it was also helpful to separate responsibilities. So in a way, we act as like the users are seeing the infrastructure of IT as a black box in a way that they just consume what we open to them, and we don't have to know what they're running on our infrastructure. But for cases like this, we interact closer, so that's why I know more about their teams. So the first use case that we worked with was a post-mortem system, which is an application to capture and analyze events emitted by the LHC and its status. This is a simple-ish Java application developed in this sector. As I mentioned, one of the requirements was to be able to roll out releases with small fixes or changes without having to wait for technical stop, to be able to like a rolling update easily, which is quite useful to do with Kubernetes.
When you say events, what kind of events are we talking about?
It's like events like information from the power converters, what is the status, like if there are any spikes, beam instrumentation events, like information that the PLCs that controlling the magnets emit. This is where my knowledge stops. I know that I know more about the requirements that have to be like extremely low latency. The connection must not break and must be always up, so that because if the connection is broken for many milliseconds, they consider that they don't control the beam and they have to stop it. For us, it's more important to know what are exactly the requirements.
You're monitoring just on the off chance that something untoward may happen, and the beam control or the controller of the accelerator then needs to respond to that.
Yes, so essentially all the systems that we deploy translate to a few screens or quite a few screens where the control operators of the CCC, the CERN control center, where they run the beam, they have to see some graphs that everything is going fine. There are no spikes or nothing outside the zone of what they expect for the graphs of power consumption or the temperature of the magnets, for example. All this translate to a screen that someone is watching and have to decide who to call, who to do what, or maybe trigger another event that will be propagated to another controller.
So you mentioned Java. Are the majority of the applications then written in Java? How can we envisage that? Or is it just across the board, any kind of language?
No, it's across the board, like any kind of language, but it had like preference in different areas. For example, for physics code, it's mostly C++ and root, which is like an extension of C++, to put it roughly to someone that doesn't know root. For IT systems, it's Python, Golang, and it used to be a little bit of Ruby. And then we have the web frameworks, which is Node.js, JavaScript, etc. And then for other kinds of applications that interact with PLCs and devices, it's Java, because usually the vendor of that device provides an SDK for Java.
Okay. That sounds quite a lot of responsibility, because ultimately without all of these systems working, there wouldn't be an accelerator, and without the accelerator, there wouldn't be any experiments. So how big is the team that you're working in at the moment, and how many people are involved in keeping the lights on, so to speak?
Whenever I get this question in a conference, for example, from other people starting with OpenStack or Kubernetes, I say that, for example, the Kubernetes team is 4 people, and the OpenStack team is 7 people. But we're not the only ones running it. We just run the components for these applications. We have a big network team, a big storage team, database team. So we get a lot of things for free from our team's point of view.
Right.
So to run all this, I would say we are at least 50, but the other teams they have other tasks as well. For example, the database team is running databases for us, but they run databases for the network team as well. Oracle database dedicated for the accelerator. The storage team is running storage for OpenStack, but also for physics, which is different. And the network team is running the data center, but also runs the campus or connection to the network of the experiments.
All the data centers and all the machines that you mentioned earlier, they're actually on campus. They're actually located at CERN, aren't they?
Yes.
They're not sort of outsourced somewhere else.
Tier 0 is the CERN data center. Then there are the farms of the experiments. In Atlas, which is across the street of the CERN campus, there are a few servers, and the new data center, of course, in Prevesan. CMS is all the way on the other side of the LHC in near EX. But everything is in the CERN campuses, or the main campus and the small ones. And then we expand, if we look at the WLCG project, to tier 1 sites, which are big research centers across the world. And then tier 2 sites that are smaller universities that participate in the collaboration.
Well, that's an entire different episode, I think, because that is it's very interesting, though. So when exactly were you a fellow? Because now you have a permanent position at CERN, I understand.
It's a limited duration, but it's a staff position.
Yeah.
And I started in 2016 for 2 years in the cloud infrastructure team. It was a collaboration with a company in Open Lab, where it's a small group in our department that handles collaboration with commercial companies to either work on software or architecture or even new devices. For example, there are collaboration with NVIDIA, with Intel, with other chip providers, or other more exotic devices that I don't know about. And I was part of a collaboration about clouds for 2 years, and then I signed a staff contract.
It must be quite exciting to work at CERN. So what's it like for you? What does your day actually look like?
As I mentioned, so many collaborations. One can imagine that there are quite a few meetings to attend.
Yes.
So we can start with a daily stand-up of the team that we sync for burning issues or heads up for the day. In the morning, 1 or 2 days per week, there is another meeting to do sprint planning and discuss where we want to go further with the service. The highlights of the day include the coffee breaks with other colleagues, which quite some time end up to be like mini meetings to discuss new ideas. But instead of the daily work, what I would like to highlight, what is really exciting at CERN is that we have so many people passing by. We have many summer students, which is a great opportunity to someone to see CERN with their own eyes. And we have like 500 people maybe, or 300 people joining every summer. We have many seminars with external people, even researchers or people from the industry, or even alumni that are successful to some other area and they come back to share their knowledge and their experience. So I think the most important part and the most exciting part for me at CERN is the ability to connect with so many communities and so many new people. Apart from the technical challenges that can be found elsewhere as well, but the exchange of knowledge, I think there are not many places where CERN can compare.
So you're working as a computer scientist in the IT department. Do you have much interaction with the physics side?
There is some interaction with physicists. As I mentioned, in the past, this interaction was much closer, but now it's more for new projects or if they want to design something bigger, or collaborations like this in the ATS sector where we get closer with not physicists, but engineers working on the specific devices for the accelerators. And for physicists, it's from time to time to set up their pipelines if there are issues with their build systems, which are quite important for them. But other than that, I think collaborations may happen in forums like the machine learning forum. I have not participated, but there is quite some exchange between computer scientists and physicists. If they want to do like a big experiment and they want infrastructure, then we get some insight to what exactly they want to run and help them build something that is not already there. For example, if they cannot use the batch system and they want something else, we come closer, discuss a bit more, and we understand better what they're doing. Otherwise, for computer scientists, it's an effort to keep up with them, to know what they're doing.
Yes, it is. So the final question, really, what's next for you? So you've been at CERN for a while. You said there's a limited contract. So what do you hope will happen in future?
I still have a couple of years in my contract. I think I will continue working here. My hope is exactly what we discussed, the second to last question, to work more with physicists, getting on board with the work they do for machine learning, because not only it's exciting, but it would be like a selfish approach for me to get into the new trend and know more about it, where I have a front seat in developments here. And then, I don't know, maybe there is an opportunity to stay here permanently or somewhere differently. And I think I would again prefer, if I had to do something else, or if I decided to do something else, to work in an academic environment again, to give back to the community, interact with people that can openly talk about what their work is and not work in business secrets and having to work for money.
Yeah, no, I understand that. There's one question actually that just popped in my mind when we talk about your workday, because there could, of course, be emergencies and every now and then things go wrong. Do you actually have kind of a shift service where you have someone on call in case something needs to be done at, in the middle of the night because the beam has a problem and it needs to be a software solution to that?
So there are different shift services in the organization. Of course, the control room has shifts. The experiments have their own shifts. And in our department, we have only for a few services, for example, the database service and I think networking. In our team, related to OpenStack or Kubernetes, we don't have because there is quite some automation to recover from failures, and failures are not that often for us in the end.
Okay. Well, thank you so much for your time, Spyridon. That was quite exciting. And I wish you all the best for the future. And hopefully you can stay at CERN for a little bit longer than 2 years.
Thank you so much.
Well, as you've just heard, there's quite a bit of action going on at CERN. If you are an ex-CERN staff member or were involved in experiments at CERN, why not join the alumni network? And for aspiring physicists and engineers, the CERN's summer schools are excellent opportunities to find out more about the exciting work that happens there. An organization like CERN has so many different exciting projects indeed, and people that there should be more than one episode about it, and in fact there will be. After the summer break, There'll be more about CERN, so I hope you stay tuned. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya!